Hello, Flat Earth researchers, debaters and debunkers. Nick here from Phuket Word, and today I want to demonstrate what I hope is the simplest way to understand how the distances measured on a level Earth are converted into distances on a globe model. So we'll do a bit of whiteboard work, and of course we'll be talking in terms of nautical miles and degrees, because that's how the coordinate system, namely latitude, has been worked out, which is then converted into a globe. But it all started with people measuring distances on a level Earth and making observations into the sky, looking at either a star such as Polaris or the sun, and then calculating the distance the observer is from that ground point. And then by having those distances using nautical miles and degrees, the angles that are seen of the stars or the sun above the horizon, a level surface, are then converted into a curved surface for a globe model. So first of all, let's just have a look at a document I put together that shows the relationship between nautical miles and degrees.
So let's just go over how these Earth distances conversions are done when we use nautical miles or kilometers, and then converting those into degrees. So we're basically basing this on nautical miles, and then the formula for converting nautical miles into normal miles would be multiplying the nautical miles by 1.151. And if you wanted to get kilometers, then you convert the nautical miles into kilometers by multiplying that by 1.852. And then to get the degrees from nautical miles, we basically divide by 60. So however you want to make out your distances or measure your distances in the first place, we end up converting into nautical miles. So you can see here, for example, that 60 nautical miles would be 69 miles or 111 kilometers, but that would only be 1 degree. Yeah? So then as we go down, we can see that 600 nautical miles would end up giving us 10 degrees. And then we go down to here, 20 degrees would be 1,200 nautical miles. Again, based on this simple formula of dividing the number of nautical miles by 60 to get the number of degrees. So 1,800 miles is 30 degrees, 2,400 miles is 40 degrees, 3,000 miles is 50 degrees, 3,600 is 60, 4,200 is 70 degrees, 4,800 is 80 degrees, and 5,400 nautical miles is 90 degrees. So you can see how using nautical miles gives you a very nice round number. Whereas if you're using miles or kilometers, then it's kind of all over the place and the conversion becomes quite difficult. Okay, so hence nautical miles being used in navigation, because they very easily convert in roundish numbers to degrees. So by that calculation, you end up with a hemisphere, or 180 degrees, that is equal to 10,800 miles, okay? And then a great circle would be 21,600 miles. That's all the way around a circle, which of course is 360 degrees. So some of you might be whipping out calculators and working out things here and there. And of course, a lot of the time, the distances are averaged out. So we have the globe Earth radius averaged to 3,440 nautical miles, or 3,959 miles, 6,371 kilometers. And of course, when we're talking about this straight line here, we don't need any degrees. All right, so that would make the globe Earth diameter 6,880 nautical miles, or 7,918 miles, 12,742 kilometers. And then, of course, by doing these conversions using pi, with either the radius or the diameter, we end up with a circumference for the globe Earth model of 21,603 nautical miles, or 24,901 miles, and 39,350 kilometers. And then the average circumference of the Earth, globe Earth, is considered to be 21,638 because they talk about the difference between the equator and the poles, with the equator apparently bulging a little bit more, but the difference is kind of negligible, so you end up with an average. But we'll be using the 21,603 nautical miles as our circumference. So again, keep in mind that these distances are measured across a level surface, and then they are converted into degrees to assume that they are part of a curved surface, equating to 360 degrees. So now let's get back to the whiteboard and see how this all works.
And have a look. Over here I'm going to put how this translates to a globe model. So first of all, let's look at how celestial navigation and working out distances for latitude are worked out. So the title is very simple: how flat Earth distances are converted into degrees for a globe model. So here we have the level surface. It could be the water, it could be the ground, and we have an observer here. Okay, he's on a boat and he's using a sextant or some kind of device to look at what could be the sun or Polaris, okay, an object in the sky that's used as a reference. So directly under that sun or star is the ground point, all right? So we're going to work out in celestial navigation terms how far this person is from that ground point. So that's basically how distances were worked out. Doesn't matter whether you assume the surface to be curved or level. Physically it's level, and it is assumed to be level like this. Now the bone of contention that globe Earth believers will have about level is the assumption that when you draw parallel vertical lines like this, that those parallel lines are not parallel. They eventually converge in the center of an assumed globe. But you have to have some measurements and calculations to get there first. So we have our guy on a boat using a sextant, and so we've got another vertical line here. So we do in fact have parallel lines, and of course we have our horizontal reference here. So the surface is horizontal, and the observer's line of sight is also horizontal. Well, you need that for the angles that you're going to measure, okay? So the way they do it in celestial navigation is we obviously, because of this horizontal here and this vertical here, we actually have a 90-degree angle either side of this vertical line, okay? So, okay, you can call this horizontal perpendicular to down, or perpendicular to vertical if you like, but horizontal it is. That's how it's done. So the person on the boat makes an observation to this sun or star, and there's going to be two angles here. There's going to be the angle between the horizontal, and that would be the observer's view of the horizon directly in front of them at eye level, and then up to here, okay, the angle of elevation if you like. But what's actually measured in terms of making these observations is the difference between the vertical and the angle to the star or the sun over here. So the reading this person might get is something like 50, let's say this angle A is 50 degrees, okay? That's the reading that they would get. So we've got our 50 degree from vertical to that star, okay? So then it's just a simple case of subtracting 50 from the 90 to get this angle here, which is going to be 40 degrees. So now with these two angles, we can work out the distance between the ground point and the observer. So let's just put that in there. Distance. What's that distance going to be? Well, as we saw earlier, we've got 60 nautical miles being equal to 1 degree. All right? So what we need to do is take this number that we worked out, the 40 degrees, okay? So what we have then is a simple equation of 40 degrees multiplied by 60, because 60 nautical miles is 1 degree. And that is going to give us 2,400 nautical miles. 2,400 nautical miles. And that is our distance. 2,400 nautical miles. Okay? So really, what's that established for us? It's not necessarily the direction, but just the distance. If we do a top-down view, let's say that we are looking down at Polaris, and we've got this, now we have this distance of 2,400 nautical miles from this ground point, and but then that could be anywhere on this circle around the ground point. Okay, so we could be here, we could be here, we could be here. Okay, that all comes down to longitude and other things, but for now we're just focusing on the distance. Okay, so over here now we can see how the distance that we measured here by the angle on the flat Earth is converted into this globe model. Now, when you're talking about latitudes or great circles, it's very important to understand that this is not a slice of a globe. It is simply a two-dimensional circle that, of course, is 360 degrees. And so from our nautical miles and our degrees, basically 60 nautical miles equaling 1 degree, we can now put these two lines, we've got these two vertical lines here that we used on the level Earth to measure the distance, and they are put here going towards the center of this circle. And so you've got, here would be where the observer is, and here is that vertical line of the star or the sun. Okay, so that would be the ground point. Okay, so this GP here is the GP here on the globe model, and here is where the observer would be. Okay, so we know that we got a 40-degree angle. So this angle here, angle B, is what is put over here. 40 degrees. Okay. So again, we've got a full circle of 360 degrees. Now, if we're talking in terms of nautical miles, that means the circumference of our circle is 21,603 nautical miles, or thereabouts. Okay. And that means that we have a radius of 3,440 nautical miles. Okay, so we're going to plug in that radius here, 3,440, because that's the only number that you can get. Nobody ever measured this alleged line or radius down to the center of the Earth. It's just that you can draw a circle with 360 degrees, and using nautical miles, then this radius must be 3,440 to give us this 40 degrees, so that we end up with a distance of 2,400 nautical miles across this arc length here. Okay, so basically, if you want to work out the arc length, the distance from this point to this point on a sphere or in a spherical coordinate system, then you're going to need the radius multiplied by the angle. Now again, we didn't have the radius, but this is just a process of doing some mathematics, isn't it? Because we've got our angle of 40 degrees, okay, and we've got our 60 nautical miles equals 1 degree. So of course we're going to get a circumference based on pi times r2 it has to be 3,440 nautical miles. Whether you consider that kilometers or the normal miles, you can convert that easily, but that's where this radius comes from, simply because we already had a distance and we only had 360 degrees. So that's what gives us a great circle. It's really just a level distance of 21,603 miles, nautical miles, converted into degrees, 360 degrees, using 60 nautical miles for every 1 degree. Okay, so that means that in 40 degrees, with a radius of 3,440, your arc distance here from these 2 points is going to be 2,400 nautical miles. Yeah? Okay, so this basically is an observation made in the sky on a level Earth, and this angle that we calculated here is now put into the center of our imaginary spherical Earth. Well, not even a spherical Earth, our imaginary great circle. Okay, so the globe model is basically made up of all these great circles that eventually give you this three-dimensional shape, because each one is separated by a longitude. So that then you get your slices. Okay, but this isn't a slice. This is just a circle of 360 degrees that represents 21,603 nautical miles in its circumference. So whichever way you want to do the mathematics, knowing that pi times r, or pi times diameter, gives you the circumference, then you're going to arrive at this radius of 3,440 nautical miles to give you 2,400 nautical miles when you have a measurement or a calculation of 40 degrees here. Again, it was based on looking at the sky from a level surface using horizontal and vertical. So yes, horizontal is perpendicular to down, but it's only made down in different directions because we've made it into an arc length. We've converted the distance into the arc length of a circle. That's the beauty of mathematics, isn't it? Because you can make these numbers anything you like. But of course, if you're going to actually put the numbers in, then they have to work out with each other. All right? But you can draw your circle any size. It doesn't have to be to scale. You just draw your lines, draw your degrees, and say that's 40 degrees. That radius is 3,440 in order to give us a distance across here, this arc length of 2,400 nautical miles. And then you can go ahead and convert it into radians if you want, and then you can use haversine formulas and make flight plans that basically take you a certain distance. Okay? But fundamentally, the latitude was based on celestial navigation. If this was Polaris, then that would put us at a distance of 2,400 nautical miles away from Polaris. We're not at the equator yet, but Polaris would have come down in our view. And so as you get further away, the angle changes, doesn't it, across a level surface. All right? And so whatever angle we end up calculating here ends up being the angle here to give us a radius and an arc length of whatever that distance is on the globe. Thank you very much.